Nobel Prize winner raises concerns. Cosmic anomalies detected by James Webb Telescope could challenge our understanding of the universe. The James Webb Space Telescope, JWST, since its launch in December 2021, has been positioned as a groundbreaking instrument that promises to redefine our comprehension of the cosmos. With its advanced capabilities, the telescope can peer back to the early stages of the universe, providing an unprecedented view of distant galaxies, stars, and planetary systems. Its launch was met with worldwide excitement, and the scientific community saw it as an opportunity to answer age-old questions about the origins and evolution of the universe. However, as groundbreaking as JWST has been, recent findings from its observations have triggered a growing debate within astrophysics. Nobel Prize-winning physicist Dr. Edward Callahan, renowned for his contributions to quantum cosmology and dark matter research, has raised serious concerns. His analysis of early JWST data points to potential cosmic anomalies that defy existing models of cosmology. If confirmed, these anomalies could lead to a fundamental reevaluation of how we understand the universe, from the Big Bang to the nature of dark matter and dark energy. In an official statement and subsequent scientific papers, Dr. Callahan explained, the data from the James Webb Space Telescope, while still in its preliminary stages, has revealed cosmic features and behaviors that challenge our current models of the universe's origins and structure. If these findings hold, we may need to reconsider some of our most deeply held assumptions in cosmology, physics, and astrophysics. The promise of the James Webb Space Telescope. Before delving into Dr. Callahan's concerns, it is essential to understand what makes the JWST such a remarkable scientific tool. Built as the successor to the Hubble Space Telescope, the JWST represents the next evolutionary leap in space observation technology. Its primary mirror, which is 6.5 meters in diameter, is more than twice the size of Hubble's mirror, giving it a much greater ability to collect light from distant objects. This makes it capable of detecting extremely faint galaxies and observing events and formations from over 13 billion years ago, nearing the birth of the universe. Unlike Hubble, which primarily observed in the ultraviolet and visible light spectrums, JWST is designed to observe in the infrared spectrum. This is crucial because the most distant objects in the universe are moving away from us so quickly that their light is redshifted into the infrared. By observing in infrared wavelengths, JWST can see through cosmic dust and capture light that has been traveling for billions of years, offering a clearer picture of the early universe than ever before. This ability has allowed JWST to detect galaxies, stars, and other cosmic structures that formed mere hundreds of millions of years after the Big Bang, potentially giving us a glimpse into the processes that shaped the universe as we know it today. Anomalies in the data. The Nobel laureate's warning. Dr. Edward Callahan's concerns stem from data gathered by JWST's initial deep field observations, which have allowed scientists to peer into areas of space that were previously inaccessible. His analysis, however, points to several cosmic anomalies that seem to conflict with current cosmological theories. Callahan's team was particularly focused on the observation of early galaxies that appear more massive and mature than they should be according to the standard model of cosmology. The prevailing theory posits that shortly after the Big Bang, the universe underwent a dark age, a period when the first stars and galaxies had not yet formed. Following this, the first structures began to coalesce in a relatively slow process, eventually giving rise to galaxies like the Milky Way. However, some of the galaxies observed by JWST show structures and features that appear too well developed for their age. These galaxies are estimated to be about 13 billion years old, yet they exhibit characteristics such as well-defined spiral arms, high mass, and mature star populations. According to Callahan, this contradicts current models of galaxy formation, which suggest that galaxies in this era should still be in their formative stages, consisting mainly of irregular clusters of young stars. These galaxies simply shouldn't exist in their present form at such an early epoch in the universe's history, Callahan remarked in a recent interview. Their mass, size, and the rate at which they are forming stars suggest that the process of galaxy evolution may have occurred much faster than our models predict, or that something else entirely is at play. The implications for the Big Bang theory. If Callahan's observations are correct, they could force scientists to reconsider the timeline of the universe's evolution, and more alarmingly, aspects of the Big Bang theory itself. The standard model of cosmology is built around the concept of the Big Bang, a moment roughly 13.8 billion years ago when the universe expanded from a singularity into its current state. This expansion gave rise to cosmic microwave background radiation, CMB, a uniform glow detectable throughout the universe, and set the stage for the formation of matter, stars, and galaxies. One of the primary issues raised by Callahan is that the galaxies detected by JWST seem to be too structured too early. If galaxies were able to form so rapidly after the Big Bang, it raises the possibility that either the universe is older than we believe, or that the early universe behaved in ways that contradict our current understanding of physics. Furthermore, there are hints in JWST's observations of irregularities in the cosmic microwave background radiation, variations that do not align with the standard model. These inconsistencies could point to unknown forces or elements at play in the early universe, or even alternative cosmological models that challenge the Big Bang paradigm. Dark matter and dark energy. New mysteries emerge. Beyond the challenges to galaxy formation models, JWST's data may also offer insights into one of the most mysterious aspects of modern physics: dark matter and dark energy. Together, dark matter and dark energy are believed to make up approximately 95% of the universe's total mass energy content, yet they remain elusive, detectable only through their gravitational effects on visible matter. Dr. Callahan believes that some of the anomalies detected by JWST may provide the first direct evidence of interactions involving dark matter. Dark matter has been one of the greatest puzzles in astrophysics, he said. We know it's there because of the way galaxies behave. Their rotation rates, for example, can't be explained by the visible matter alone. But we've never directly observed dark matter. The anomalies we're seeing in the Webb data might be our first indication of dark matter at work in the very early universe. Some of these anomalies involve discrepancies in the mass and velocity of galaxies compared to what would be expected based solely on visible matter. Callahan posits that dark matter may have played a more direct role in the formation of these early galaxies than previously thought, perhaps even catalyzing their rapid development. Dark energy, the mysterious force responsible for the accelerated expansion of the universe, may also be implicated in JWST's findings. If the telescope is detecting variations in the rate of expansion over different epochs of cosmic history, it could suggest that dark energy is not constant, as current models suggest, but fluctuates over time or interacts with other cosmic forces in ways that we don't yet understand. Multiverses and alternative theories. A new frontier? One of the more speculative, but nonetheless intriguing, implications of the cosmic anomalies detected by JWST is the possibility of alternative cosmological models, including the idea of a multiverse. The multiverse theory suggests that our universe is just one of many, each with its own set of physical laws and constants. Some theorists believe that certain anomalies detected in cosmic background radiation or galaxy formation could be evidence of interactions between our universe and other universes. While Callahan is cautious about endorsing such ideas, he acknowledges that the anomalies may point to unknown physics that could include interactions beyond our universe. It's too early to say whether the data we're seeing supports the idea of a multiverse, but we certainly need to keep an open mind, he said. If nothing else, these findings suggest that the universe is far more complex than we previously imagined. Another possibility is that the anomalies are evidence of new particles or forces that we have yet to discover. Some physicists have speculated that JWST's observations could lead to the discovery of previously unknown forms of matter or energy, which could help explain the mysteries of dark matter and dark energy, or even provide insights into the nature of gravity itself. Reactions from the scientific community. Dr. Callahan's concerns have sparked widespread debate within the scientific community. Some researchers have praised his willingness to challenge established models, viewing the anomalies as an exciting opportunity for new discoveries. Others, however, urge caution, pointing out that the JWST is still in its early stages of operation, and its data should be carefully vetted before drawing any definitive conclusions. Dr. Susan Myers, an astrophysicist at NASA's Goddard Space Flight Center, emphasized the importance of further observation. While the data from JWST is certainly intriguing, we need to be careful not to jump to conclusions, she said. Anomalies in early data are not uncommon, and it's possible that these discrepancies could be explained by more mundane processes once we gather more information. Dr. Callahan, for his part, welcomes the debate, insisting that the anomalies, whether resolved or not, provide a critical opportunity for advancing our understanding of the universe. Science is about questioning assumptions, he said. The data we've gathered from JWST is complex, and it may take years to fully understand. But if we don't confront these anomalies head-on, we risk missing out on what could be the most significant discoveries of our time. The road ahead, a new era of discovery? As the James Webb Space Telescope continues its mission, the cosmic anomalies detected in its data will remain a focal point for researchers. Whether these discrepancies ultimately lead to a paradigm shift in our understanding of the universe or can be explained within the existing framework of physics, one thing is clear. JWST is pushing the boundaries of what we know and forcing scientists to rethink their most basic assumptions. For Dr. Edward Callahan and his colleagues, the next few years will be crucial in determining whether these anomalies signal a revolution in cosmology. Regardless of the outcome, the ongoing exploration of the universe with JWST promises to yield insights that will shape the future of astrophysics for decades to come.